All right, moving on, we'll look at analyzing the graph of rational functions. So we're going to talk about the characteristics and use those characteristics to help us build a sketch of this graph, f of x equal to 3x squared minus 3 divided by x squared plus 2x minus 3. So you can see in a rational function, we've got two polynomials that are being divided. We've got a numerator polynomial of 3x squared minus 3 and a denominator polynomial of x squared plus 2x minus 3. All right, your first step before you begin should be to go ahead and factor the numerator and the denominator and see if you can reduce this rational function. So in the numerator, we can go ahead and factor out, for example, we have a GCF, greatest common factor, of 3. So I'm going to go ahead and bring that out. So as we factor out the 3, we'll be left with x squared minus 1. And with x squared minus 1, we have a difference of squares, so we'll be able to factor that too into its two linear factors. Now in the denominator, I'm going to go ahead and break this quadratic up into its two linear factors, which we can see easily looking at it because it has nice integer factors. We need x and x up front for the x squared term. We know our constant term. We want a factor combination of 3 that'll add up to the middle term, 2x, when we do our outer and inner product. So with 1 and 3 being its only factors as far as integers go, this is a prime number. Right, luckily those do work. So we could put a 3, for example, here on the outside, and we could put a 1 here on the inside. And as we do that, right, we have a plus with the 3 and we have a minus with the 1. Our outer product would be 3x, our inner product would be negative 1x, which adds up to 2x, and negative 1 times 3 is negative 3. So if you distribute or fold that out, you're going to get x squared plus 2x minus 3 back. Now, in the numerator, we're not done factoring. So notice, again, we have a difference of squares. So I'm going to go ahead and factor the difference of squares. We know that a squared minus b squared factors to a minus b times a plus b. So with x squared minus 1, we got x squared minus 1 squared. So it's two linear factors, or x minus 1 times x plus 1. And now, if you notice, in our numerator and denominator, we do have a common factor. So we can reduce this rational function. And that common factor is important. It plays a role in the graph of our rational. But we're left with what? 3 times x plus 1 divided by x plus 3 as we reduce that or simplify it. Now, as we move on, let's go ahead and state what we found from this. With that said, we have a common factor. So this common factor, right, produces our whole. So I always want to recognize, so the common factor, we want to find the 0 from it. So 0 of common factor. Implies whole in graph at that location. So let's go ahead and find that 0. So I'll go ahead and do that first. So for example, x minus 1, the common factor, equals 0 when what? X equal 1. So there's a whole right here at x equal 1. Right, which is an undefined value, right? It's a point of discontinuity on our graph. We're breaking our graph at that location. Now, with that said, let's go ahead and find out what y would equal. Let's get the ordered pair. So to find y, let's go ahead and evaluate our function. So that implies we would find the value of this function with x equal to 1. And that'd be 3 times what? 1 plus 1, as we take out x and plug in 1, over 1 plus 3. And as we simplify, we got 3 times what? 2 over 4. So I got 6/4, which reduces to 3/2. So there's our y coordinate. So there's our y value. All right. So y is equal to that, x equal 1. So that implies, right, our whole will be at the ordered pair of 1 3/2. So as you notice, it did ask us to find any holes in our graph. So I'll go ahead and answer that down here. I like to go ahead and find out that first. So there'll be a hole in our graph at 1 1.5, right? We plotted that point. Get point of discontinuity. All right, now as we go to domain, that ties into our domain also. So domain are all the real number values of x that satisfy this function. So we know also with this rational function, right, we cannot have a denominator of 0. So again, we know restrictions. We cannot have x cannot equal 1. We've already mentioned that as the whole. And also x plus 3, right, which is in the denominator, cannot equal 0. So that implies x cannot equal -3. So our domain, right, so there are two restrictions. So our domain would equal all real numbers except -3 and 1. So let's go ahead and I'll write that if you want. We can go ahead and show that on an x line if you need to, right? So if you were looking at our graph at -3 and 1, right, we're going to have breaks in our graph. So our domain are all these real numbers except those. So all x values less than -3, right? All the x values greater than -3 but less than 1, and then from 1 to infinity as our domain, right? Domain restrictions. All right, with that said, let's go ahead and talk about the zeros of this function. So the zeros, which would be your x-intercept locations. Zeros, and again, I'll make that mark, x-intercept locations in our graph. Now to find zeros, we do what? We let f of x equal 0 and solve for x. So let's go ahead and do that. So in our function, let's go ahead and write down our reduced function. 3 times x plus 1 divided by x plus 3. Well, let's set it equal to 0. Now, as you work in a rational function, right, we clear out the fraction. So in our next step, well, we go ahead and multiply both sides by x plus 3. Right, as we clear out the fraction, we all know how to solve rational equations. Right, we're solving for x. We got to get x out of the denominator. So as we do that, right, we're left with what? We're left with 3 times x plus 1 equal to 0. So in rational functions, right, you're going to be setting your numerator equal to 0 because 0 divided by anything is 0. So you can see as it reduces, we'll be able to solve easily. So what's that imply? So that implies what? We can divide out 3 on both sides. That implies x plus 1 equal 0. So you set your factors equal 0 and solve for x. So we have a 0 at -1. So there's our 0 of this function. So it asks to find our 0. And that also implies what? So that implies, I'll write with that, the x-intercept. So we'll have a point -1, 0, which our graph will cross through the x-axis. So your zeros and your x-intercepts go together. And speaking of intercepts, let's move on to y-intercept. So to find y-intercept with any function, we let x equal 0. So that implies we got to evaluate our function at 0. So f of 0 is equal to, well, we can plug it back in. Now you can plug it into the reduced function. If you want, you can plug it in the original function as far as that goes. But 3 times 0 plus 1 over 0 plus 3. Which is 3 times 1 over 3. So I got 3 over 3, or 1. So there's our y-intercept location. There's y. So that implies we have a y-intercept at 0, 1. So we have a x-intercept at -1, 0. We have a y-intercept at 0, 1. So we're finding points which we'll be able to use, right, this information to sketch our graph. All right, let's find the equation of the horizontal asymptote. So horizontal asymptotes are equations of imaginary horizontal lines that are going to shape our graph. Now the most we can have is 1. So again, a horizontal asymptote, again, is an equation of a line that we're going to use to help shape our graph, and it's going to be a horizontal line. Now, with that said, we need to compare the degrees of the polynomial to see if you have a horizontal asymptote come into play. So compare the degrees, right, of your polynomials of numerator and denominator polynomials. So with that said, let's go back to our original function. So remember, we had f of x. So here's our function. F of x was equal to 3 times x squared minus 3 divided by x squared plus 2x minus 3, right? So if you look at comparing the degrees, so as we look at this function, our degrees, of course, are the exponents of the leading terms. So that implies the numerator polynomial, so numerator degree, is equal to 2, and our denominator degree is equal to 2. So our degrees are the same. Well, if our degrees are the same, so as we compare these two, right, they're equal to each other, they're the same. So if numerator degree equal same degree as the denominator degree, I'll make a little note. How we've abbreviated in our lectures, N and M. We'll call N the numerator degree and M the denominator degree. So again, N equals M. Well, if N equals M, we have the same degrees. We have a horizontal asymptote. That implies our horizontal asymptote exists. All right, so N equal to M or N less than M. So if our numerator and denominator degree is the same, or if our numerator degree is less than our denominator degree, we do have a horizontal asymptote, which means we have a horizontal line that's going to help shape our graph. Our graph, again, is going to flatten out horizontally that location in certain parts of the graph. So let's go ahead and talk about what that horizontal asymptote would be. Now, again, it's the equation of a horizontal line. Now, with the degrees being the same, it's always equal to the ratio of the leading coefficients. So our leading coefficients in this problem, we had a 3x squared with a leading term and a 1x squared in the denominator. So our ratios, all right, ratio of leading coefficient. Let's go ahead and write that down here. So anytime the degrees are the same, ratio of leading coefficients, is where our graph will flatten out horizontally. Now, if the degree of the numerator is less than the degree of the denominator, all right, it'll flatten out at y equals 0, the x-axis. And if n is greater than m, or if numerator degree is greater than the denominator degree, you do not have a horizontal asymptote. So again, we compare degrees. There's 3 possibilities. They're the same, or numerator is less than the denominator degree, or numerator is greater than the denominator degree. Less than or equal to, we have 1. If it's equal, it's a ratio of leading coefficients. If it's less than, it's the y equals 0 x-axis, y equals 0 line. So again, that's a horizontal asymptote. So when we graph there in a little bit, we're going to use this line to help us sketch the graph of this function. Now, how about the vertical asymptote? So vertical asymptote is an equation of vertical lines that shape our graph. And with that said, vertical asymptotes come into play with our undefined values, right? The zeros of the remaining denominator factors. So finding the zero. So vertical asymptotes, again, location of the zeros of the remaining denominator factors. So when I say remaining, after we've reduced, right, one of our denominator factors canceled out, x minus 1. That's where the whole came in. So that implies we had a remaining denominator factor of x plus 3. So with that said, let's find its 0. As we solve for x, we're going to get x equal to negative 3, right? One of our domain restrictions. Well, yeah, with vertical asymptotes, they're the undefined value location, right, of your remaining factors after you've reduced. With that said, there's a break in your graph at this location. It'll never touch these lines. So these are undefined locations. So that implies our vertical asymptote, right, is the vertical line x equal -3. So again, asymptotes are equations of lines, right? Imaginary lines are going to use to shape our graph. So our graph will go vertical at -3 on the x-axis. It'll get closer and closer and closer to that line. We'll never touch it. It is an undefined value, so your denominator is 0. So keep that in mind, right? Zeros are the remaining denominator factors. Now, with all of this information, let's go sketch it. So we've got this information here now that we can use to help us graph this function. So let's go ahead and do that together. So I'm going to go ahead and build in my x and my y-axis. All right, and we're going to gather in the information that we found. Now we have found a x-intercept over at what? X-intercept point was at -1, 0. So I'm going to go ahead and plot -1, 0. And we had a y-intercept at 0, 1. So I'm going to go ahead and plot 0, 1. And then we have a vertical asymptote at -3 on the x-axis. I'm going to put this in a different color. So over here at -3, let's draw in this imaginary vertical line. So to do that, we're going to draw in a dashed line. Because remember, this is not part of the graph. This just shapes our graph. It gets closer and closer and closer. So here's the line, or the vertical line. So there's that vertical asymptote. Okay. With that said, we also had a horizontal asymptote. So let's go ahead and draw that in. And our horizontal asymptote was at 3 on the y-axis. So let's go to 3 on the y-axis. And let's draw in the horizontal line. As we draw that in, right, it's an imaginary line. Not part of the graph, only used to shape it. So there's our horizontal asymptote. There's the line y equal 3, right, which was the ratio of the leading coefficients. And what else did we find? We found a hole in our graph, right? Our hole in our graph was at 1, right? 1 2/3, 1 3/2 to be exact. So I'm going to plot that point. So right 1, up 1.5. So right in here, I've got a hole. Let's show that hole. Draw it in here a little bigger. So right 1 up. So here's the hole in the graph. So there's 1 3/2. So our graph has a hole in it at that location. Now to sketch it, we got to figure out, all right, what happens with these lines. Now we know the vertical line it can't touch. One thing I do want to find out is this horizontal asymptote, does our function ever intersect it? So determine any intercepts. So determine if function intersects the horizontal asymptote. So what we do, we take our function and we set it equal to 3. So as we do that, now we can go back to our original function where we reduced it. So we got 3 times x plus 1 divided by what? X plus 3. And let's go ahead and solve that for x, see what happens. So again, we're solving a rational. We're going to clear out the fraction. So we can go ahead and multiply both sides by x plus 3. And they divide out. And you'll see again as we reduce, we have 3 times x plus 1 equal to 3 times x plus 3. And what happens is we simplify. We get 3x plus 1 equal to 3x plus 9. As you solve that for x, notice the x terms end up eliminating out. So we end up with an equation that reads 1 equal to 9, which is not true, right? So that's a false statement, right? Implies no intersection. We can't find a intersection point. So it doesn't intersect. So we know it'll never touch that line y equal 3. So let's build our graph. Now let's see what happens. We do need a couple points to get some detail. So look at a point. Let's see what happens on the left side of the vertical asymptote. So I'm going to use an easy integer value like -4, a test value. what is that value? Let's go find f of -4. So let's plug that in real quick. So in our function, we got 3 times -4, right? All this in parentheses, plus 1. There's the numerator. Divided by -4 plus 3. As we simplify, I got 3 times -3, right? -4 plus 1, divided by -1. And when we simplify that, what do we get? We get -9 over -1, which is equal to 9. So looking at our graph, right, we know our graph will, what? There's the y coordinate, there's y. So that implies we have a point -4, 9 on this graph. So I'm going to plot -4, 9. So -4, 9 be somewhere up here. Left 4, up 9. Now, with that said, we can go ahead and sketch it. So we know y equal 3, it flattens out, never touches it, right? No intersection with it. And it goes vertical at x equal -3. So there's the two asymptotes. Sketching in that part of the graph. So remember our domain, all x values less than -3. Well, there's that region. That's what our graph is doing, right? As it approaches these asymptotes, it gets closer and closer and closer and closer, but never touches. All right, definitely doesn't touch the vertical, and we've concluded it will not touch the horizontal either. Well, what happens to the right of -3 and between this hole too? We got a hole in here. Let's see what we got with this. Well, we've already got points over here, so we don't have to find any points on this side. We've got our x-intercept and our y-intercept. So if our graph goes vertical at -3, never touches it, has to pass through -1, 0, 0, 1, has a hole at 1, 3/2, got to jump over it, and then approaches 3 and flattens out horizontally. There's your graph. So we've sketched our graph just using the asymptotes and our intercepts, and of course any holes, we need to make sure we locate those. So that's sketching graphs by building their characteristics, using that to graph your functions. So we'll take a break. Hope that helps. We'll do another one here in a minute, our next example.